Today in this video, we are going to study about alkenes of BSc Part 1 Organic Chemistry. Those hydrocarbons in which two carbon atoms are joined together by double or triple bonds are known as unsaturated hydrocarbon. Those unsaturated hydrocarbons in which the two carbon atoms are joined together by double bond are known as olefins, since halogens form oily additions compounds with them. Compounds having 2, 3 and more double bonds are known as alkadiene, alkatriene and alkapolyenes respectively. Alkenes have general formula CnH2n. Due to the double bond in alkene, the presence of two carbon atoms is mandatory. The simplest member of the alkene is ethylene, that is C2H4 or ethylene, and we can call it in IUPAC it is known as ethene. The presence of double bond in alkene is known as olefinic or ethylenic bond. Due to the presence of double bond, alkene is more reactive than alkane. The members up to C4 series are ethene, propene, but1-ene, but2-ene and 2-methylpropene. Now let's see the structure of the double bond. 1 sigma and 1 pi bond are present in ethene. Its bond energy is 146 kilocalorie per mole. Bond energy of a sigma bond is 83 kilocalorie per mole and bond energy for pi bond is 63 kilocalorie per mole. So we can say that pi bond is weaker than sigma bond. The carbon-carbon bond length in alkene is 1.34 angstrom. Due to the presence of double bond, alkenes show geometrical isomerism. That is, because of the double bond, they cannot rotate about the bond like they can in the single bond. If there is a single bond between the two atoms, then there can be a rotation along that axis, but due to the double bond, the rotation is restricted. Now we come to the nomenclature of alkenes. So let's discuss some rules. Select the longest carbon chain which contains double bond. These compounds are derivatives of parent compound. On the basis of the number of the carbon atoms in main compound, the corresponding alkane, the suffix "ene" is replaced by "ene". That is, compounds having double bonds are known as alkenes. So if we take the example of a member containing 3 carbon atoms, so the alkane will be propane, but its corresponding alkene will be formed by replacing the "ane" of propane by "ene", so it will be known as propene. So if we see certain examples, they are, this is a heptene derivative, as this is the longest chain is of 7 carbon atoms. This is a pentene derivative, this is a hexene derivative, and this is again a pentene derivative. Now we come to the second rule. The presence of the double bond in parent compound is considered on that carbon atom from where the double bond starts, and the numbering is done from that end which gets lowest number. The position of the double bond is shown in its name, capped in between alk and ene. Like we saw in the previous case, it was but1-ene. So but is for alk and then one number and then ene. Besides double bond, if substituents are present in parent compound, then the name and position can be represented similar to alkane. The names of following structures are given as, if we consider them. The first example is 3-methyl hept1-ene. This is 2-ethyl pent1-ene. This is 3-ethyl hexene, and this is 3-ethyl pent1-ene. The third rule is, if a compound has 2 or more double bonds, then that chain is selected as parent compound which has all the double bonds or the maximum number of double bonds. The suffix "ene" of these compounds are prefixed with the word di, tri and tetra on having 2 or more double bonds in parent compound. The numbering starts from the end in which the sum of the position of the double bond is lowest. For example, if we take this example, this is but1,2-diene and this is but1,3-diene. Now we come to the isomerism. The first two members of the alkene series, that are ethene and propene, do not show isomerism, but other members of the alkene series show structural and geometrical isomerism. Compounds with molecular formula C4H8 shows both types of isomerism, that is, position and chain. Isomerisms of alkenes up to 4 carbon atoms and the IUPAC and trivial names. If we consider the first member, that is C2H4, its structural formula is, as we have seen, CH2CH2. Its trivial name is ethylene and its IUPAC name is ethene and its boiling point is 169. If we consider the second member, that is C3H6, then its structure is CH3CH double bond CH2. Its trivial name is propylene and its IUPAC name is propene and its boiling point is 225.3 Kelvin. The fourth member is C4H8 having 4 carbon atom and it shows isomerism. The first isomer is CH3, CH2, CH double bond CH2, which is known as alpha butylene, and the IUPAC name is butanene. And if we consider the second isomer, this is CH3, CH double bond CH3. Its trivial name is beta butylene and its IUPAC name is but2ene. And its third isomer is CH3C, and the C is bonded by a single bond to CH3 and with a double bond to CH2, and its trivial name is isobutylene and its IUPAC name is 2-methyl propene. If we consider the but2ene, we see that it shows two geometrical isomers. This one is cis form and this one is the trans form. But1ene and but2ene show position isomerism, while the 2-methyl propene shows chain isomerism. Now we come to the method of preparation. First method is by dehydrohalogenation of alkyl halides. When alkyl halides react with ethanolic KOH at high temperature, it forms corresponding alkene. Removal of the HX from the adjacent carbon atom is known as dehydrohalogenation. Hydrogen atom is removed from the carbon atom and the halogen atom is removed from the adjacent carbon atom. This is known as 1,2 elimination. That is, the hydrogen and the halogens, they are removed from the adjacent carbon atoms. If sodium ethoxide and alcohol or tert butoxide or tert butanol is taken, then the yield will be high. So if we consider the reaction, then this is a general alkyl halide. It reacts with KOH in the presence of ethanol and the product is alkene. So if we consider this specific example, that is CH3CH2CH2Br, then the Br from the terminal atom is removed and the hydrogen from the adjacent carbon atom is removed and the resultant is propene. If we consider this example, that is CH3CH in which the Br is at the secondary carbon atom, so the Br is removed from this secondary carbon atom and the terminal hydrogen atom is removed and the resultant is propene, that is CH3CH2. Now if we consider this tert butyl bromide, then we see that this bromine gets eliminated from the tertiary carbon atom and one hydrogen atom is eliminated from the adjacent carbon atom, and this dehydrohalogenation yields isopropene. And it is seen that ease of the dehydrohalogenation of different alkyl halides is in the sequence that tert alkyl halide dehydrohalogenation reactivity is faster than the ease of the secondary alkyl halide, and the ease of the dehydrohalogenation of the secondary alkyl halide is higher than the ease of the dehydrohalogenation of the primary alkyl halide. Secondary and tertiary alkyl halides on dehydrohalogenation give high yield. Many alkyl halides on dehydrohalogenation form more than one type of alkene. Low yield of alkene is obtained from primary alkyl halide. Ethyl bromide on reaction with ethanolic KOH forms ethene only. Some alkyl halides form more than one alkene. For example, if we consider this case of 2-bromobutene, then we see that 2-bromobutene on reaction with ethanolic KOH forms 80% 2-butene and 20% 1-butene. Now we come to the mechanism of the dehydrohalogenation of the alkyl halides. The reaction in which two atoms are removed from a molecule is known as elimination reaction. In such reactions, two sigma bonds break and one new pi bond is formed. Elimination reaction occurs by two types of mechanism, that is E1 and E2. Dehydrohalogenation of primary alkyl halides mainly takes place via E2 mechanism. Kinetic studies reveal that E2 reactions are of second order, that is rate of the reaction depends upon concentration of the alkyl halide as well as concentration of the base. This means that E2 reaction is one-step process and occurs with the formation of the transition state. The hydroxide group of alcoholic KOH acts as strong base which absorbs proton from beta carbon atom. The carbon-hydrogen bond breaks and a new carbon-carbon pi bond begins to form and the leaving group from the alpha carbon begins to depart, which results in the formation of a pi bond. An important point for elimination reaction is that they are always accompanied by substitution reaction as well. Thus, in this reaction we see that some amount of propanol is also formed as substituted product. Now we come to the E2 reaction. It is also known as bimolecular elimination reaction. 2-bromopropane reacts with sodium ethoxide and forms propene. Rate of the reaction depends upon both concentration of the 2-bromopropane and ethoxide ion. So we see that 2-bromopropene reacts with ethoxide ion in the presence of alcoholic KOH and propene results, and this rate of the reaction is given by the concentration of the isopropyl bromide and also the concentration of the ethoxide ion. That is, the rate of the reaction for this depends upon the concentration of the 2-bromopropane and also on the concentration of the ethoxide base. So it is concluded that transition state formed in rate determining step uses both alkyl halide and ethoxide ion. And it is seen that as the covalent bond formation starts between OC2H5, that is ethoxide ion, and beta hydrogen, the double bond formation starts between alpha carbon and beta carbon, and the bromine atom departs with its electron pair as bromide ion. In this way, a transition state is formed. As the alkyl group on alpha carbon atom increases, the rate of the reaction increases. The reactivity order of the alkyl halide is in the following order. That is, the reactivity of the methyl halide is lower than the reactivity of the primary alkyl halide, and the reactivity of the primary alkyl halide is lower than the reactivity of the secondary alkyl halide, and the reactivity of the secondary alkyl halide is lower than the reactivity of the tertiary alkyl halide. Now we come to the E1 reaction, that is unimolecular elimination reaction. Secondary and third alkyl halides show even reaction. For example, third butyl bromide, when heated with alcohol, undergoes dehydrobromination to form isobutylene as elimination product and third butyl alcohol as substituted product. Kinetic studies reveal that this reaction is of the first order kinetics. That is, the rate of the reaction is proportional only on the concentration of the alkyl halide. E1 reaction is two-step process which involves the formation of the carbocation in the first step. This is a slow step and hence it is rate determining step. The second step involves a loss of proton and alkene is formed. This step is a fast step and hence does not affect the rate of the reaction. When third butyl chloride is heated at 298 Kelvin in 80% aqueous ethanol, so 83% substituted product and 17% elimination products are formed. In both substitution and elimination, first step is the formation of the third butyl carbonium ion. This is the rate determining step. So here we see in this third butyl chloride, the chlorine atom is eliminated as chloride ion and third butyl carbonium ion is formed. Now substitution or the elimination depends upon the fast step that follows the slow step of the formation of the carbonium ion. If we consider this substitution reaction, then it is seen that if after the formation of the carbonium ion, the solvent molecule attacks on positively charged carbon of carbonium ion and forms third butyl ether and tert-butyl alcohol as substituted product, then it is SN1 reaction. And if it consider elimination reaction, then if solvent molecule after the formation of the carbonium ion in the first step acts as a base, it abstracts hydrogen in the form of proton and forms 2-methylpropene as eliminated product, then it is considered as E1 mechanism. E1 and S1 mechanism takes place simultaneously. In the presence of strong base and high temperature, mainly elimination reaction occurs. 2-methyl-2-butene is formed by dehydrobromination of neopentyl bromide. The mechanism of the reaction can be explained. This is a neopentyl bromide and this undergoes elimination of bromine atom as bromide in a slow step and bromide ion and primary carbonium ion form. Now this primary carbonium ion which is formed in the slow step undergoes rearrangement and gets rearranged in the form of a stable tertiary carbonium ion. Now this tertiary carbonium ion reacts with a molecule of alcohol whereby this alcohol abstracts one hydrogen atom from the adjacent carbon atom of the carbon which carries the positive charge and 2-methyl-2-butene is formed along with the protonated alcohol. Now this protonated alcohol reacts with the bromide ion and forms ROH and HBr. This is all for today. Thank you.